Hello, welcome to this video produced as part of the Further Maths Support Programme as material for A-Level Maths and Further Maths. This is the third in the series on motion with variable force. Again, I remind you that suvat shouldn't be used in this sort of work because the acceleration will not be constant any more than the force is. This time we look at force as a function of velocity. So again, we'll start off where we were before. We're looking at particles moving in a straight line. We're interested in what it is that determines the variation of the force, if it's not going to be constant. And we have three options: that it's dependent on time, on displacement, or on velocity. And as the highlighting in red implies, this one is about velocity. So let's take our problem. We've got a particle of mass 0.1 kilograms. It's released from rest. It falls under its own weight. After times t seconds, it's moving with v meters per second, with the downwards direction being positive. And there's an air resistance of 0.02 v newtons. So we have a force diagram before. The first part of it here indicates the way x is measured. It's positive downwards. We've got the velocity showing, and we've got the two forces, the one up and the other down. So this will lead us to a simple force diagram. If we take F equals ma, taking positive as downwards, the force is 0.1 g minus 0.02 v, and that is equal to the mass times the acceleration, which is 0.1 times, we'll call it a for a moment. Now in this context, we know that a is going to vary, so we need to include a in an appropriate form so that we can integrate. So let's do two things at once. Let's multiply everything by 50, so we'll get 5g. 0.02 is a 50th, so it will be minus v is equal to 5a, but I'll replace a by dv by dt. Now we've got no x's complicating the left hand side this time, so dv by dt is quite acceptable, especially as we want the velocity as a function of time. So that's set up to separate the variables. So we can say that if we take the t's on the left, the integral of dt is equal to the integral of 5 over 5g minus v integrated with respect to v. So that will give us then an integral which is a log, so we'll get t is equal to, and if we guess, it's log 5g minus v, and the only way that's wrong is we've got a minus sign. So we're taking the 5 that's in the numerator, we'll have minus 5 log 5g minus v, plus a constant, of course. Okay then, so that takes us to where we've got to at the bottom of the page there. That's the expression we've just got. So now what can we do with that? Well, we need to think in terms of pushing that a bit further, so we can change it to being, we can put in the initial conditions. So if we take when t is equal to 0, that the velocity is equal to 0, that will tell us that we get 0 is equal to minus 5 log, and it will just be 5g on the brackets so that it's unambiguous, plus c. So our c is 5 log 5g. 5 log 5g. So if we subtract this line from the line at the bottom of the page, we'll end up with t equals minus 5 log 5g minus v, and we can put in brackets minus log 5g. So that tells us that we've got minus 5 log, and it will be a division because the subtraction of logarithms corresponds to division. So we have 5g minus v over 5g. And that finally tidies up by putting the t with the minus 5 with the t, so we have minus t over 5 is equal to log 5g minus v over 5g. Okay then, so that's set up now for the next step, which would be to take exponentials. So that's the summary of the story so far. A little more compactly so that we've got room to carry on. So now we can say that the e to the minus t over 5 is equal to 5g minus v over 5g. Now we want to get that in the form v equals, so if we multiply by 5g, we'll have 5g e to the minus t over 5 is equal to 5g minus v. That's getting there now. So if we put the v on the left and the 5g times the e bit on the right, we get v equals 5g minus 5g e to the minus t over 5. And so that can be more economically expressed as 5g bracket 1 minus e to the minus t over 5. Now expressing it that way shows, we're not asked this, but expressing it that way shows that if you let t get larger and larger, so the exponential term tends to 0, the velocity is approaching 5g. It will be a terminal velocity type situation. So if we put g as 9.8 in, that 5g will turn into 49. So let's do that on the next slide. We got as far as there, and now we put in g as 9.8, so our final answer is v is 49 times the bracket with 1 minus e to the minus t over 5 in it. Well, that's what the question asks us to get, so we have finished, but we can speculate where it might go beyond that. If we used a equals dv by dt, that we did use a equals dv by dt to get the expression we've just got, we could instead have changed the dv by dt to v dv by dx. Now if we did that, that was our basic working, that's a quotation from where we got to before. If we changed the dv by dt to v dv by dx, then, well, that's all that's happened there. At this point we can still separate the variables, but this time we'd end up integrating with respect to x on one side and v on the other. So that will look like that when we've separated the variables, and you can see that on the right hand side it's not this time going to be a log well, it will be partly a log integral, but it's going to be somewhat more complicated, but it's still a standard integration problem. So we come to a halt at that point, having indicated that as a possible further development. And that brings us to the end of this video presentation. The next one will look at a variation of the one just passed, in which we use a different model for the form of the air resistance.